Okay, so again, there are going to be lots of overlap with grade 11. That's why I'm going fast as a review. But there are some parts that might be new, so get to it. Oh, you didn't grab one. Okay, 5.1 is going to focus on the primary trig functions. You should have done sine and cosine already. Depending on your teacher, you may not have done tangent. I might have not done tangent with my class either. So that might be new. But with your knowledge and your identities with, I guess, your trigonometric identities, you know that tangent is basically sine over cosine. So if you have these two charts filled in, you're basically good with tangent function as well. Unfortunately, I don't have time to get you to graph it by yourself and discover tangent. And so I'm going to work through it with you. All right, please take a look at these values. Here is a sine function, and I created a chart based on 0 all the way to 2 pi. In other words, 1 cycle. The first section, I did it using angles or rotations that you are familiar with. And then I started moving in pi over 4 increments. The reason why you know there's a 0, 1, 0, -1, and then 0, sorry, you go back to 0, is because the sine ratio is y over r. When I am here, what is my y value? 0. So that's 0 over r. When I'm here, my y value is 1, and my radius is 1. So that's why it's 1 over 1. When I am in 180 degrees or full pi, what's my y value? 0. So 0 over r is 0. And when I am here, 3 pi over 2, my y value is a 1, -1, and my radius is a 1, so that I have -1. And then I go back to 0. That should be familiar to all of you. The reason why we get this kind of funky up, down, up pattern. Any questions to clarify? Because I could be wrong. Is this transforming my unit circle into a function? Is that unfamiliar to anyone here? Because if not, then I need to make sure that I'll talk about it a little differently. A little bit? Okay. Think about it this way. You know that we start from the x-axis, and then we are rotating up in a counterclockwise direction with a radius of 1, right? And that means my point here would be 1, 0. Up here at pi over 2, my angle is pi over 2. My point would be 0, 1. And at angle of pi, my point would be -1, 0. And at 3 pi over 2, my point would be 0, -1. Kidding me. Of all times to start running out of. Okay, at -1. Let's pretend that's a 0, that's pi over 2, that's a pi, that's 3 pi over 2, and that's a 2 pi. You can't even see that. All right. Notice, for a sine function, you already know it's opposite over hypotenuse, therefore y over r from our unit circle. What is the r value here? Well, the r value is always a 1. What's my y value? 0. So when it's sine of 0 degree or 0 radians, that is equal to a y value of 0 over a radius of 1. At angle 0, my point is 0. With me so far? At sine of pi over 2, what's my y value? 1. It's 1 over a radius of 1. It's a 1. So sine of pi over 2, it's a 1. Do I go any higher? No, it makes sense because if I trace my path around a circle, what do I get for sine of pi? The y value is 0 and my radius is 1. It's a 0. So at sine of pi, I get back to 0. Then what happens? Go ahead, Yusuf. At 3 pi over 2, what's my y value? -1 over a radius of 1, it's -1. So at 3 pi over 2, I get a -1, and then I'm going to go back to 0. If you were to calculate pi over 6, pi over 4, pi over 3, and then pi over 2, you will see that I get about halfway, closer, closer, and it actually traces out the curvature of a circle. Yes. Yeah, of a unit circle. Yeah, that's absolutely right. Right? Because what is the height here? It's a 1. What is the height here? Is a 1. It's the same idea. And because of coterminal, you can go over and over and over again. Doesn't mean we don't have to finish at 2 pi. We can go 4 pi. You can go 6 pi, right? And therefore, we call this a periodic function. It repeats. It's, like a periodic table in science. You constantly repeat. You go to the next line, next line, next line. Same thing. It repeats. This part right here repeats again and again and again every time we go around a circle. And this is what we call a sinusoidal function, because it looks like a sine wave. It's a special word, sinusoidal. Okay, so that's essentially grade 11 recap. And so I'm going to graph this a little bit more in detail. I hope you can keep up. Here we go. If you use your calculator or you use your special triangles, sine of pi over 6 will get you 0.5, half. Sine of pi over 4 would give you, which is approximately 0.7. And then this is √3, and then it goes to 1. And then this is again 135 degrees or 3 pi over 4. I did it in the increments that you know. Let's graph this point. 0. And then at pi half, I get 1. And in between, what happens? 30 degrees or pi over 6 is about here. And then there's pi over 4 and then pi over 3. There's 3 points that are very close to the dotted line in between. Half is found at 30 degrees or pi over 6. And then I have, I think 0.707. Yeah, I think so. And then about an 8.6, something like that. When you look at these dots, you see that they are starting to slow down in height, increasing in height as we approach 1. It's going to look something like this. And with your knowledge of circles, consider what happens next. 3 pi over 4, you plug that into the calculator, or you use CAST rule, you will get √2 over 2, then a 0, and then you'll get negative √2 over 2, and then -1. You get -2 √2 over 2, and you get 0. If I were to graph this, we are getting here 0, -7-ish, 0.7-ish, -1. You get these points. I will wait for you to make a connection where all these points are. So my question to you is this. If you know that it's supposed to graph out a circle, right? But just of course, like half of a circle and then half of a circle. How many points do you actually need to draw a relatively good sketch? Zach? 8? It could be. What if I was very, very flexible? Like I'm not gonna slam you for communication marks for it. This is just for your eyes only. How many points would you need to draw a relatively good graph? Well, a regular curve here. One with the zeros, here, here, and here. Right, so starting from the middle, highest point, back to the middle, lowest point, and back to the middle, sort of like this. From here, if I repeat, this part came from the lowest point, and then it went from 0, and it probably came from the highest point, and it came from that. So if I have these 5 x's, can you sort of trace out a rough circle? That's what I want you to get to. If I have every single point here, of course you'll be able to graph it. And I will do that now. Of course you'll be able to do something like this, and it continues going on and on and on. Can you do the same using these 3? Try to draw as nice of a curve, half like, you know, Sky Dome, Rogers Center Dome, as best as you can, right? Like, doesn't have to be perfect. And same with these 3. And of course, draw the arrow because it continues on and on and on. So notice why it's periodic. If I take this as a snapshot and I cut and paste over here, I get the exact same thing every 2 pi. Okay. Just for my knowledge, who here finds this still relatively new? Don't be embarrassed, it's okay. A little bit? Okay, just has an idea, okay. So there are still people who would forget? Okay, so maybe I can't rush it as much as I thought. I'm gonna have to change the location of my break. That's okay. As long as we leave today with the knowledge from grade 11 as a review, I'll be very satisfied. Highlight one cycle, sure. You can use a pen for those of you who don't have an actual highlighter. You can do something like this. And notice how it doesn't go past 1 and -1. So you don't have to do anything more than that. Highlight one cycle, that would be one cycle. State the domain, the range, the period, amplitude, and then highlight the transversal or the mid-axis of this periodic function or the sinusoidal function. Let's do it. Domain. I'm sure you'd have guessed it by now, but x belongs to any numbers. There's no limitation. But for range, there is a clear limitation. What's my range? Oh. Yep, at the same time, right? It has to be in between, which makes sense. Take a look at the unit circle. My radius is a 1. It makes no sense for the y value to be any bigger than that. Otherwise, we're not dealing with the unit circle here, right? So you could do an interval notation. So y belongs to -1 to 1. Or you can totally do -1, y in between, a +1, and there it is. Either one I am okay with. You're communicating the same information to me. I'm not testing you on squiggly lines or whatnot. Period. How large is the period? Well, that's basically how long does it take to go through one full circle? Nothing has changed. That's going to be 2 pi. Amplitude. Amplitude, please note that you can argue that the amplitude is a negative one, but right afterwards we have a positive one, and then right afterwards the amplitude is a negative one from the midline. So amplitude is simply, you can think about it as an absolute value. I don't want to see a negative for amplitude. Just tell me the value of how high or how low it goes from the midline. And if you're not sure what the midline is, it is right there. The proper term, if I remember correctly, is the transversal axis. It's the mid-axis. And the equation for that, as you might guess, is just y equals 0. It becomes important when we graph in 5.3. So I'm introducing these terms, especially if you haven't seen them before. Transversal is a special word. If you want to call it the mid-axis, I'll be okay with that. But sound more mathematical by saying transversal axis. Any questions? This is the sine curve. No? Okay. I'm going to ask you, yes? Mactinman? It could be Mactinman. Well, I am hoping that you'll be able to figure it out from your abilities to graph, because to me, they are one and the same. And if you forget the formula, you can still figure it out. But let's cross that bridge when we get there. Cosine. If I gave you the values for cosine, I'm wondering if you can graph it for me. So instead of writing all this, which we can, and I already did on my answer key, if I didn't, and I gave you the values, remember, cosine is equal to x over r, right? And if you apply my points from my previous example, cosine starts from a 1, and then at pi over 2 becomes a 0. At pi, it becomes -1. 3 pi over 2 becomes 0 and goes back to a 1. I'm wondering if you can draw this curve without any of the points in between. Now, I will write the numbers very small, but I don't think you need it. Try it first. Try it first. So at 0, a radian of 0, I start at 1. At pi over 2, I have a 0. At pi, I get -1. At 3 pi over 2, I get 0. And 2 pi, I get a 1. And I could repeat that again on the left side. Can you draw a cosine curve? And please don't draw straight lines. It is not where we're going. Okay, you're not drawing a V here. Do you see the semicircle using these 5 dots? Or rather, do you see the semicircle with just this? Let's draw that first. The other 2 parts are going to be quarters of that same circle. It's going to look like this. It's going to sort of look like that that I don't know emoji with that little happy face, you know, putting their hands up. You know what I'm talking about? No, the ASCII one, the alt code one, with the face that's like sideways and has a weird smile and then saying, I don't know what you're talking about. You guys know, am I being a nerd? Okay, never mind. Anyways, please don't draw straight lines. You need to be comfortable at this point in creating cosine and sine curves on a whim without even thinking. because you're supposed to have a lot of practice from grade 11. Okay. So I'm intentionally not going to fill this in because I want you to get to a point where you can see it without so many accuracy points. In my answer key, the values are there. So if you do care and you're a bit of a completionist and it sort of bothers you, either do it on your own or check out my answer key online. Highlighting one circle, once again, this would be one circle, one cycle. Okay. Highlighting one cycle, state the domain, same thing. X can be any real number. State the range, same thing. Y is going to be an interval of -1 to 1, or you can say, this is true. The period, same thing, it's going to be 2 pi. Just because it's cosine doesn't mean it's not a full circle. Amplitude, same thing, it's a unit circle, so the value is still 1. And draw the transversal, y equals 0 is still the mid or transversal axis. All right, decent pace, everyone, decent pace. Okay, I'll wait another minute. If you are done copying, I'm gonna actually leave tangent off on the side and do that last. I wanna go to the back page and do the reciprocals. 5.2, so this is basically 5.1, you're done. You need to be aware of certain things, yes. Mm-hmm. But here's a couple of things before we move on. Here's some things that you will see in the future, and mark my words, you will see it very soon. If I asked you using cast rule, when is sine theta equal to half? Sine theta is positive. That means where would you see this angle appear? Sine angle is positive. Austin? Quadrant 1 or quadrant 2? Take a look. In my sine function, half is right here. If I draw a dotted line at y equals half, where does it intersect my curve? This location and this location. Guess what? If this was a unit circle, that would be quadrant 1 because this is 0 to pi over 2. And this is quadrant 2. This is pi over 2 to pi. So whether you use cast rule and a circle, or you think about it from a graph, it's one and the same. Give me another number. If I said sine theta was equal to -1/2, where would you see that? Well, CAST, you would see it here, or you would see it here in quadrant 3 or 4. Well, guess what? If I mark sine equals -1/2, you will see it in quadrant 3 and quadrant 4. They're all sort of together. It's all the same thing, okay? Any questions about that? The reason I tell you this is there will be a case where, let's pretend this is a Ferris wheel. Let's pretend this is a Ferris wheel that's 1 meter tall and 1 meter low. This is a 2-meter diameter Ferris wheel, which is like this big, so it's tiny. It's for like babies, okay? A tiny Ferris wheel for babies. What if the question asks, when will the Ferris wheel be above the ground, above like 1 meter in height? Get what do you see where this is going? If I gave you a curve, right? And I said, this is hypothetical. If I gave you a question, I'm like, here is the floor. Here is my Ferris wheel's path. When will the Ferris wheel reach 2 meters if this was 0? Well, it reaches 2 meters at that point, doesn't it? I'm going to start taking this curve and start applying it to real life situations that repeat again and again. Typically, it's going to be a wheel. It could be ocean, right? High tide, low tide. What are some other things that repeat? I don't know. Yes. What? Sure. It could be a roller coaster. And I say, hey, when will the roller coaster dip underneath 50 meters or something like that, right? It's all going to sort of connect to each other. So I just wanted to let you know. Let's talk about reciprocal. What was reciprocal again? You don't have to write this down. If I said f of x was equal to x squared plus 1, don't write this. Don't write this. What is the reciprocal? Yep. Or like I changed it now. 1 over x. Perfect. What is something you have to watch out for when you do a reciprocal? Something that you didn't have here, but suddenly you have here. That restrictions, yeah, asymptotes. When do I get an asymptote? Not literally, but just generally. Going once, going twice. Hinda? When the denominator is 0, which means I get a vertical asymptote when the original function equals a 0. How many places do I see a 0 for sine function? 1, 2, 3. If I do the reciprocal of sine, you're going to get vertical asymptotes. Turn the page. I am going to do cosecant because it is a reciprocal of sine. So I sort of purposely did it like this. You can take the bottom of the sheet and lift it up. And you will see that sine of 0 is 0. So anytime you see a sine of 0, your cosecant will be undefined. It's a vertical asymptote. Where else? Where else do you see a 0? Pi and 2 pi. Those places are going to be undefined. Next, you know, all the points that we placed in the previous section, write the reciprocal, flip them. So this one's going to be 2 over 1. For now, I know it's wrong, but just do 2 over root 2, 2 over root 3, 1, 2 over root 2, you know, so on and so forth. Okay. This is going to be 2 root 2 over 2. Oops. I got in such a habit. 2 over root 2, 2 over root 3, that's a 1. 2 over root 2, negative 2 over root 2, negative 1, negative 2 over root 2. Please note, it's really hard to graph this, so I'm going to write it down. 2 over root 2 is approximately 1.4. And 2 over root 3 is approximately 1.15, close to a 2. Or please note, this part is not grade 11. This is actually grade 12. You've never done a reciprocal of sine, cosine, and tangent before. So be flexible. This is what cosecant functions look like. Here we go. I am going to draw a vertical asymptote at 0, pi, 2 pi. And seeing as how the sine function repeats on the left side, where else do you think you will see a vertical asymptote? Think about it. I'm going to use pink. Vertical asymptote. And then pi, vertical asymptote. 2 pi, vertical asymptote. I will also see a 0 in the sine function at negative pi and negative 2 pi. You're going to see a vertical asymptote here, a vertical asymptote here. Next. Brace yourselves. Let's do the easy ones. At pi over 6, which is just left of the first dotted line, I have a 2. And then on the dotted line, I have a 1.4. And then just to the right of the dotted line, I have a 1.12-ish. And then at pi over 2, I have a 1. And you think you would continue going lower, but at 3 pi over 4, this is 3 pi over 4, I go back to a 1.4. What do you think that's going to do as I approach the vertical asymptote? Yeah, it's going to look like this. Yep. Now I'm going to graph these 3 points and see if you can guess where the next curve is going to be. At 5 pi over 4, it's going to be negative 1.41, 1.4, and then 1, and then negative 1.4. Oh, no, that's not it. Put that one back. Where do you think that one's gonna go? It's gonna, using your logical skills, I suppose, considering how a curve, as I went upwards, went upside down like that, it's gonna mirror image. So maybe, and it will, if you do enough accuracy points, we'll do something like that. As a hint, I'm not sure if yellow will show up, but a sine curve is this right now. You see that? Sort of? Yeah. That's a sine curve. This is the reciprocal. Looks messed up. And so a sine curve, you know that it's going to repeat every 2 pi. It's going to do this. So what do you think it's going to look on the left side of the y-axis? Same thing. Yeah. So if you have the patience, go for it. I'm going to do x here at a 1.4, 1.4. X here, negative 1.4, negative 1.4. There is your cosecant curve. You know? Sine x. Yeah. No, the end behavior doesn't act that way. You wouldn't say it's an oblique asymptote. I just wrote the yellow there to show you where the sine curve is. And if I take everything, divide it by a 1, some interesting things happen. If the maximum point of a sine curve is a 2, then the reciprocal would be, well, it depends. It doesn't necessarily mean it's going to be 1 over 2 sine. It could be 2 times 1 over sine. I think it depends on the question. I don't think we have the same picture in our heads right now. So you can ask me afterwards, okay? Highlight one cycle. Same thing right now. It repeats every 2 pi. State the domain. It gets a little funny. Domain could be anything, but what? What's the restriction? All these pink lines. This is what you can say. X can be anything. However, X cannot be 0 and every multiple of pi. X cannot be a 0 plus any multiple of pi. So I'm going to say pi times k, where k belongs to an integer. K could be a 0, k could be a 1, k could be a 2. So it could be 0 plus 0. So X can't be a 0. It could be 1 pi. It could be 2 pi. It could be 3 pi. It could be 4 pi. It could be 5 pi. It could also be -1 pi. It could be -2 pi. It could be -3 pi. It's part of an integer family. Yes? It would be. The reason I show you this is because it's going to be very important when we get to 5.4. So just exposing it to you. No, show it to me using this. Well, you could if you want. Every integer multiple of pi. You can write that. I'm writing this because it saves you time and headache, right? Yes. Pi k, I need to know what k is. You can say pi k and then comma k belongs to integer. Yes, k belongs to integers. Sure, I guess so. Yeah. Range could be y belongs to anything, but whatchamacallit? Y has to be less than or equal to a -1, or 1 must be less than or equal to y. So in other words, the bottom side and the top side. Yes. Pardon me? The side? Sine? It will be completely opposite of sine. Yeah. I suppose, yeah. Well, sine has to be contained within -1 and 1. Cosecant has to be bigger than 1 bigger than or equal to or less than or equal to. Yes. Oh, sure. I will take a green. One cycle would be just 2 pi's worth. Basically that, just one cycle. And you can imagine secant is the exact same thing, except the location of my vertical asymptotes are slightly shifted because the location of the zeros for cosine is slightly shifted. So again, I'm going to flip back to my sine and cosine curve. Take a look. For my sine, a 0 was at 0, pi, and 2 pi. That's 3 zeros. For a cosine, because it's shifted over, I have 2 vertical asymptotes where there wasn't in the previous. Okay, so it's literally the exact same numbers, but everything, just as how the sine curve was shifted over to make cosine, cosecant will be shifted pi over 2 over to make secant. So I'll do this very quickly. 0, I have a 1. I don't care. This is undefined. And then I have -1, undefined, a +1. I will draw my asymptotes. And this is where I hope you will get to very, very soon. Seeing that there is a pattern, you'll be able to, starting from here, you'll be able to reproduce where the vertical asymptotes are anywhere on the map. You will also be able to identify where the point is a 1. So in this case, it's a 1. And at pi, it's a -1, which means here it would be a 1. And then down here, it would be a -1, and up here it would be a 1. And just from these points alone, you have an idea of where the curve is going to go. Because not only can you do this one by one, but if you know what cosecant looks like, it's derived from essentially the same curve, except it shifted pi over 2 to the left. So it should look something like that, 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 like that, and like that. Yep.
So will our vertical asymptotes always be the same? Like if we're doing post, we're doing reciprocal post, the vertical asymptotes are doing the same slot.
Same slot as
For like where cos is 0 for become the
yes,
vertical asymptotes.
yes.
Really like okay.
Okay. Same thing with domain, range, and period, same idea. It's basically the same thing, but let's go through it because your domain, you can use some extra practice. X can be anything for the domain, but we have asymptotes. Where? Pi over 2 and additional multiples of added by a multiple of another pi. So X cannot be pi over 2 or pi over 2 with an addition of a multiple of pi. And the range, same thing as before. Y cannot be or well, I forgot period, but you know that the period is 2 pi. Oof. That's already an hour. Time is flying. Your butt's probably itching right now. Okay, I'm gonna have to change this up a little bit. Let us finish off tangent and we'll go for our walk. Yes.
These two graphs,
Mm-hmm.
no longer asking for the transversal axis. That one is not for still 0, even though numbers or even though you have.
No, there's no necessarily any. There is no necessarily any mid-axis for this. I suppose we could define it, but at least in our level right now, it's a waste of our time. And you will see that if you are working with sine and cosecant and secant, it actually is easier to convert it into sine and cosine, just like for trig identities, and work with that. There's so many more useful information that comes out when you do that. Yes?
Why is your mean always greater than or equal, less than or equal to 5?
Well, you take a look at it. You will never see a green marker in between this space. No green streak.
I see that with the pattern. Why.
It all comes from sine and cosine. Is there ever a situation where sine and cosine gets larger than a 1? Right? In other words, if you flip it, there will never be a time where the value gets smaller than a 1 or larger than -1. So this part no longer is, you can think about that as a relationship. Any other questions for secant and cosecant? Yes. Sure. I mean, typically I would do from 0 to 2 pi. That's a little not nice, right? You can, yeah, as long as it's any cycle. So you can start and finish your cycle anywhere you want. So I would recommend in this case, why not just do this? Something like that. A cycle does not have to start at 0 radians. That doesn't make any sense. Okay. All right, people, tangent, hang in there. Whew. So this, who here has seen a tangent curve? Oh, from school or just because? Huh? School, really? Who? That's why. Nathan, what about you? Mister?
I'm sorry.
Oh, he showed you. Okay. You know how to draw it?
I don't know how to draw it.
So again, I'm going to take this slow because it's probably new to everyone. I'm going to write out everything. And just like before, we are going to plot all these points. But once you see where we're going, I'm hoping that all you need is like 3 accuracy points and you'll be able to eyeball it nicely. Okay, here we go. Tangent function is sine over cosine. So I'm going to ask you, I'm going to keep my camera here, but I'm going to ask you to literally place this number on top of this number and tell me what the value is. I'm going to ask you to put this fraction, that fraction, and ask me what the value is. That, and I realized I didn't finish writing it. This is a 1. That is a root 2 over 2. That is a negative. And that is a negative root 2 over 2. And that is a positive root 2 over 2. So this is for cosine. Say again?
Are the two raised?
These ones?
Yeah.
No, this is root 3 over 2. Yeah. I'll write it bigger. There. Again, I will focus the camera just on the tangent section. I'm going to ask you to, whether you can do it in your head or use a calculator, figure out 0 divided by 1, half divided by root 3 over 2, so on and so forth. And you should see a pattern. Easy. Who wants to volunteer for the easy one? Go ahead, Mason. 0. Amazing. But 1 over 2 divided by root 3 over 2, 1 over 2 divided by root 3 over 2 is the same as multiplying with this. Can you do it in your head? 1 over root 3. Oh, I didn't hear it. Next one, Root 2 over 2 divided by itself, 1. Root 3 over 2 divided by, oh, half. What am I doing? Sorry. That's not a 1. Shame on me. That's a half. Because they should be opposite of each other. Root 3 over 2 divided by half. No, for now, you don't have to. I'm just trying to show you what the curve looks like. Based on, or if you don't like doing that, we can also use our special triangles. What is tangent of pi over 6? 1 over root 3. What is tangent of pi over 3? Root 3 over 1. Let's draw this. 1 over root 3 is 1 divided by 1.7, pardon? 0.57. And this is 1.73. So 0, 0.57, 1 second, 1, and then 1.73, and then an asymptote. Yes. Say that again, sir. When you do transformation, AKDC. Remember AKDC of transforming functions? No. Vertical stretch, horizontal shifts. Oh, we're gonna do it with me. Yeah, my class would have seen it. Do you remember me telling you about the box method? Oh.
It was a long time.
I might not have because it was COVID. I might have, because I was like rushed for time. I might not have actually shown you. But yeah, anyways. All right. So, interesting. Using this pattern, I am going to calculate the remaining values. -1, 0, 1, undefined. -1, 0, 1, undefined, so on and so forth. It is. At 3 pi over 4, I get a -1. I get a 0. And then I get a 1. And then I get another. And then I get another -1, a 0, a 1. And then I should get another. There. So some of you might be tempted, oh, do I just draw straight lines between the 3 dots? That's why I did the first 3 points here. It's not actually a straight line, it's a curve. It moves like this. It's a good question. What do you think would be on the other side? Yeah, well, sort of. It's a circle, right? This part and this part, they're going to continue to repeat again and again and again. If you consider these values of a sine and cosine curve, they're going to be the same, but it's on negative sides, right? Negative directions. You would be correct if you guessed maybe that it would mirror itself on the opposite side. And this funny curve repeats itself again and again and again. To the point where Hopefully you only need 3 accuracy points. And then you have an idea of this curvature. Again, it won't come to you right away through lots of practice and sort of looking at a graph and just being very, using the graph a lot or drawing the graph often is how you'll get sort of used to this and being able to sketch it very quickly. Because of our situation, because of COVID and all that jazz, you won't see too many questions where it asks you to sketch a tangent curve like from scratch. But you at least should know what it looks like in the case that you encounter a question that asks you to visualize or to sketch something along these lines. Yes?
Okay, so why we're dealing with like an interval between pi over 2 and pi over 2, or point zero, minus 1, 0, 1, and then between minus pi over 2, it's 0.57. Like why after?
It's because I graphed it that way. After doing 30 degrees, 45 degrees, and 60, I just wrote in 45-degree increments.
Oh, okay.
I'm just saying, yes, you can do these points, but if you didn't have them, do you see that it's 0, 1, negative 1, 0, 1? Yes, I just want to show you that it's not a straight line, it's a curvature, and you're gonna reproduce that in your head.
Oh, like those points minus 1, 0. Yeah, kind of reactors.
Correct. It was for your knowledge. It's not that it was, the curve is not changing. Okay? It was just for you to see. Okay, highlighting one cycle. One cycle in this case is 1 pi. Take a look. One cycle would be just that. What is the domain? Well, it could be anything except pi over 2 plus multiples of pi. So x could be anything, but x cannot be pi over 2 with any multiples of pi. Range, well, this one's easy. Y could be anything we want. And the period in this case is going to be just pi. Any questions? Yes. Cotangent, for whatever reason, the graph decided not to. But if you think about it, take a look. If you flip this, it becomes undefined, right? What if you flip this? Flip a 1 over 0. 0 over 1, right? So this becomes 1 over 0. This becomes 0 over 1. This becomes root 3 over 1. This becomes 1 over root 3. Do you notice that there's like a mirror image that's going on? Yeah, the cotangent is basically this. It's basically that. So maybe that's why the textbook decided, you know what, they can figure it out at university or whatever. They don't really specify it. And again, tangent curves, not that popular in questions because it's not as applicable in real life, whereas sine and cosine. I mean, you could apply it, but this is above both of our pay grade right now. Yes?
So that means we're not even going to.
You should know it because if you reach that pay grade, you shouldn't be caught with your pants down.
How about we're not going to reach that pay grade this year. So we gotta worry about it.
That makes no sense. It's like, yo, I might fight in the future, but I'm not fighting now. So I'm not going to learn how to fight.
No, how do we, okay, where's Cosecant?
Like, I'll paint a masterpiece later. I'm not painting a masterpiece now, so I'm not going to learn how to paint. Nah. Huh?
One of these scenarios, you get beaten up in about 5 minutes.
Uh-huh.
So you don't have to like really.
What? You know what?
Okay, but there's no example of Cosecant.
Moving on. We're going to go for our break right now. When we come back, we're going to go straight into another review of transformations. And I hope that I could introduce another quick and easy method that I hope will save you time. Like my goal is that everyone will be like, whoa, that's it. That's so easy. And then they just use it. If that's not you, that's fine, whatever. We'll practice it as best we can. And then cross fingers, start a little bit of 5.4. Any questions?